Ever wondered how deep learning works? Today we unravel the mystery behind this cutting-edge technology. Deep learning is a fascinating subset of machine learning, a key pillar in the world of artificial intelligence. It has been at the forefront of many recent breakthroughs, from self-driving cars to voice assistants and beyond. Unlike traditional machine learning, deep learning has the extraordinary ability to learn from unstructured and unlabeled data, making sense of complex patterns that humans or even other machines might miss. It does this through artificial neural networks, inspired by our own brain's biology, creating layers of interconnected neurons that process and learn from data. But how does it do all of this? Well, it's a step-by-step journey from defining the problem, collecting and preparing data, to designing the neural network architecture, and finally inference. To understand deep learning, we first need to understand the process it follows. Ready to dive in? Deep learning is not a one-step process, but a series of steps that lead to the ultimate goal of making accurate predictions. Let's embark on this journey together, understanding each step along the way. We begin by defining our problem. What are we trying to solve? Is it a classification task, a regression, or maybe clustering? Having a clear understanding of the problem at hand is the foundation upon which we build our deep learning model. Once we know what we're dealing with, we need to gather our materials, in this case, data. Collecting a large representative dataset is crucial. We then roll up our sleeves and clean this data, handling missing values, outliers, and other inconsistencies. We also split our data into training and validation sets, ensuring we have a solid base for our model to learn from. Next, we pre-process our data to make it suitable for input into a neural network. This could involve normalizing or standardizing numerical features, one-hot encoding categorical variables, and scaling the data. Now comes the exciting part, designing our neural network architecture. We decide on the number of layers, the type of these layers, and the activation functions for each layer. Think of this as the blueprint for our deep learning model. With our blueprint in hand, we initialize our model parameters. We set the weights and biases of the neural network. Proper initialization is like a head start in a race. It helps the network converge faster during training. Then, we define our loss function. This is a measure of how far off our model's predictions are from the actual values. The choice of the loss function depends on the nature of our problem. We also choose an optimization algorithm at this stage. This algorithm, whether it's stochastic gradient descent, ADAM, or RMS prop, will adjust our model parameters during training to minimize the loss. We're now ready to train our model. We feed the training data into the neural network and perform forward propagation to make predictions. We calculate the loss and use back propagation to update the weights and biases, aiming to minimize that loss. This process is repeated for multiple epochs until our model converges, but we're not done yet. We then evaluate our model's performance on the validation set and adjust hyperparameters based on this performance. This is akin to fine-tuning a musical instrument, ensuring it plays just the right notes. We then assess our model's generalization performance on a separate test set. This provides an unbiased estimate of our model's performance. After testing, we fine-tune our model based on the results. We may adjust the architecture, tweak the hyperparameters, or even gather more data to enhance performance. Finally, we reach the inference stage. Here, we deploy our model to make predictions on new, unseen data. It's like sending our model out into the world, armed with the knowledge it has gathered. Deep learning is a journey, not a destination. It's a continuous process of learning, adjusting, and improving. The beauty of deep learning is in its ability to adapt and improve over time, providing us with increasingly accurate results as it learns from more and more data.